This paper was presented at the JCT Traffic Signal Symposium 2024, thanks to our media partner Highways News, and sponsored by AGD Systems, Four-Way Consulting, Traffic Group Signals, Smart Micro UK, TRL Software, PTV Group, Census Networks, and Starling Technologies.
Good afternoon. Good afternoon, everyone. So we only have a few minutes, and the paper contains all the technical detail. So this is going to be a lighter overview to explain the concept. I'm going to go quickly at the start because I need to spend a bit more time on the slides towards the end. So I started developing this idea about a year ago for a junction at Aylesbury. I wanted a scoot control option that would react immediately to queuing. Around the same time, I was studying how the Svarco controller is programmed, particularly with regards to the gap out bit. And it was really good because Svarco informed me that I could edit one of the files myself and rerun it through the simulator or emulator without having to go back to the configurator each time for every minor change. So I used it like a development platform. I just needed an old Windows 7 PC, so don't throw your old PCs away. You never know when they're going to be useful, but you don't connect them to the network. Right. So I thought I'd start with a chronology of major traffic innovation for a bit of context. I'm really sorry I missed out Mover. I knew I was missing something, but I couldn't picture it at the time, and this was a while back. So Mover should definitely be on there. I haven't pushed the button, have I? Sorry, I did press it, but not hard enough. Right, so it's 50 years of continually evolving innovation. I'll have a quick glance, and you can see it goes back. It's 1970s. So, but I think we've overlooked something. So that's the question. How do we control internal network queues that can block a junction? And the answer is introduced in 1967. It is not even old technology, it's zero technology from a bygone era. Actually, I was around then. And predates all the innovation I've just listed. And I think it's a bit embarrassing. And if you want to know what the enforcement looked like in 1967, there. So I think we're due an update. So the consequences of our current practice, I mean, if you look at that list, I'm not going to read them out, but all those things are contrary to good design practice, and we would never build anything that had those attributes. The RAC did a survey of drivers, and 80% said they struggled to clear box junctions, and half had accidentally got stuck in one, and the main reason they cited was bad driving by other motorists. Make of that as you will, but I think we've all been in the situation where somebody's pinched your gap just as you committed to go, and you end up stuck. And so effectively, we make it difficult for our customers to use our products, and then some authorities fine them when they make a mistake. In case you're wondering, no, I haven't had a ticket. But I really don't like box junctions, and I think it says to drivers, work it out for yourselves, because we can't control the traffic properly. So what should we do? Well, fundamentally, let's end the green signal before the exit from a junction is blocked. And let's also be a little bit happier about using special conditioning. I've often sensed the reluctance to get involved with special conditioning. And let's look at advances in queue detection capabilities to make sure that we really are detecting a queue. So within Scoot, we have various methods that are available, and I'm not going to describe them here because this isn't a Scoot course and I don't have time, but if you concentrate on the right-hand side, they're just not good enough for what I needed them for. Acting too late, imprecise, complicated, and I don't want to be terminating Scoot, going to another mode and coming back in. So that's what I wanted, something that was going to act immediately and stay in Scoot and not be too complicated. And I think it's this. So a recap of the gap out bit. Now, colleagues at TfL, I think you call this PED Advance, but it's extremely underutilized. And so in most cases, if you do what I'm suggesting here, then you won't be losing any functionality. And it's a bit that sits on the control word with the force bits. And it's set optionally. You can leave it out in the plan just by adding +go. Now, this used to be just an exclamation mark, but it's changed in UX recently. So is a drawing, and we like drawings. So in this case, the controller's just terminated stage 1. You can see the amber light on. The stage terminated because Scoot was sending in the controller F1 and F2 +go. So the go bit affects the stage change code in the controller so that holding the stage becomes dependent on the VA detectors. So when the VA detectors gap out, the controller makes an early change to stage 2, even though the Scoot plan would have normally kept the stage running longer. And in the moment, I'm going to show you why I think this go bit is the bit we've all been waiting for. And it was always there, but we just weren't making the best use of it. So this is based on the Swarco controller. So I need to speak to Unix and the others and find out how we can do it with their controllers. But the structure is this. So the code is divided into 2 parts that interact. I think we know what a demand is. It comes from detectors and it comes from F bits in the Scoot plan. Now inhibits, this is really important because it's what's determining the timing. It holds the current stage, preventing a stage. Preventing a change in the stage. So both bits are being set and cleared independently. They're independent of each other, and they form the stage change logic of the Swarco controller. That's the bit that I'm going to concentrate now. So, so you can think of the inhibit as a brake on an automatic car. That's a really good analogy. So here we have both feet down. They may or they may not be my feet, but the stage demand is being demanded by the throttle being pushed to the floor, and it's being inhibited from moving by the brake being pressed at the same time. And that looks like that, yeah? Yeah. So when we then release the inhibit, we can go, yeah? So that's the brake released suddenly. What happens? Now there's a prize for anyone who wants to embark upon a bit of audience participation and add sound effects for this. I've got a couple of prizes. So that's what happens, yeah? So that's your inhibit being released and you go. I think that's a good way to think about it. So now I'm going to be brave and I'm going to try and do some Boolean algebra with you. And I don't know, this might work, it might not, but I'm around anyway. So you've seen that picture before, but this time I've added a simplified explanation of the code. And I'm going to have to read it directly, because if I get this wrong, it's just going to confuse everyone. So, so the horizontal bar over a term means not. It's the inversion. And remember, you can only have 2 states, true or false, otherwise known as 1 or 0. And we can use these interchangeably, whatever is easier. So in that expression, when go is off, which it certainly is when you don't use it, the term not go is true. Yeah, because not 0 is 1, or not false is true. And that makes the whole bracket true, reducing the inhibit to the force bit ended with 1, which is just whatever the force bit is. So that's with go equals naught. Another way to think of it is the inhibit is just the force bit, which can be 1 or 0 on or off, and that's what we normally see. But in this case, we've actually sent the go bit to the controller, so go equals 1 or true. So not go is false. And so for the bracket to be true, we need extensions running to be true. And when the extensions terminate, the whole bracket is false. Sorry. The F bit is ANDed with the bracket, which is false, so the whole expression is false, which switches off the inhibit, so the stage changes. Now we've got it you've been waiting for. So this is another sketch which I changed the last term of the expression to not Q detected. Not is really important. So as we can see, these cars aren't ULEZ compliant. But when the go bit is off, it functions in exactly the same way as the other case, with just the false bits holding an inhibit on. But when we set this one, set the go here to 1, then not, and you're looking at the second line of the code, not go is false, because go is 1 and not go is 0. Yeah? And now the inhibit, to hold the stage, that bracket needs to be true, which only happens if not Q is true. In other words, there's no Q. And as you can see, the amber light has come on as the stage is terminated because of the Q. So if that was too much, you've got headaches. So in other words, when the go bit is set, the stage continues while the F bit is on, or until a Q is detected. Now we have the Swarco emulator. So I don't know if you're familiar with this, but you can see at the top, I'll use the mouse thing, right? So this is where the F bits come on, and is it big enough to see? You've got F1 and F2, and then go is over here somewhere. The mimics for the phases is down here, and then around about here is the DQ bit. I'm going to set it going, and this runs twice. So if you miss it the first time, you can see it again. So it's in stage 1, and you can see phase A is on, and F1 is currently activated. Now we've got F2 joined it, and the next thing is going to be go. Right now we're looking down here for DQ. Ding. Right now we have a call delay of about 6 or 8 seconds to speed it up. Watch A. Right, A is just terminated. So going to go through again. Let it go through stage 1. Slightly speeded it up. So you don't get much quicker interaction than that to a queue. And it's all within SCOOD. So going back to are we in stage 1 yet? Oh yeah, it's ticking over. Back to stage 1. F1 is set. F2 is going to join it. Ding, right, so now go is going to come on. And now the DQ bit for this particular one. Right now, countdown, watch phase A, top amber, it's down. There you go. So, final recap. Let's move that out of the way. So the details of the derivation of the code, if you're really interested are in the paper, and I'm just trying to keep it simple today. Remember, this works for Swarco controllers. It's been a really useful open platform to develop with. And other manufacturers may implement their logic differently. I need to speak to them. So I have a couple of Unix controllers I need to do this to. So the gap out bit is underutilized anyway, so repurposing it doesn't really lose any functionality. And I think it's going to be particularly useful for signal control roundabouts where you have a 2-stage arrangement. I've already used it, or starting to use it for a case that's slightly more complicated, and I've got other iterations of it in the pipeline, but one thing at a time. Yeah, so any questions?
Thanks very much indeed, Andy.
Yeah.
Any questions for Andy?
I've got one, if I may. would it be too simplistic to say that and this might mean something to some of the audience, but there's when you're building CLF plans, there's a CLF group influence that I've never used called Prevent Except To.
Yeah.
Does the GO bit effectively doing the same thing? Or have I thrown you?
You've thrown me a bit because it's a while since I've used CLF.
Well, then Prevent Except To, my understanding of it, and I hope it's right because I've been teaching it on the advanced course for quite a while, is that what you can do is you can send effectively an F bit, or it'll be a G bit or whatever. A move to a stage bit if you like. But if you put Prevent Except To on, if it gaps out, it'll actually go back early.
Right.
So it's the same concept.
Yeah.
All right. Okay.
But this is something. Yeah. So I mean, if we can be sure that we have detected a queue, and we might need multi-zone detection for this, then it's got a lot of promise, I think. And you have to site the queue detector quite a distance from where you think the queue is going to end up, because you've got to get through the call timer, and then all the traffic that's come from the stop line is in the junction, it's got to pile up, and you really don't want to be forcing that queue to stop in the junction every single time. So it's quite far ahead from where you think it is. Okay. We have an SVS detector waiting to be used there, and I understand we can vary the detection position, so I'm going to be playing with that and see where we get the best results from, and maybe I'll come back next year and tell you if it works or not.
Fantastic, thank you.
Deal?
Thank you. Actually, my question relates to the queue. I was going to ask, the position of the detector for the queue. How does that fit with Scoot? Because Scoot detectors are, generally, further down the link, which is good from what you've just said.
You put a specific detector in for the queue, so it's not necessarily the Scoot detector. I've got one. I am actually using it for the next node, but I might double it up. I've got loads of inputs ready on this configuration to move them apart. And on this particular one, I'm actually doing queues in both directions, and there's a hierarchy of stage to call. I have to put in a contingency stage, which will be called by queue in one direction, and that's got a little bit more complicated because I've actually had to play with the demand code as well. I've had to use the inhibit to cancel the demand for stage 2, so it jumps from 1 to 3 in the Scoot plan, even though it could have done both. It always wanted to do sequential if it could. So it's just getting a bit complicated, but I needed to keep it simple for me to be able to explain it.
So essentially you'll need an extra loop, presumably.
Yes.
Okay. Any more questions? Well, given the time, I think we must move on. Thanks very much indeed.